In this quick clip, we look at how a self-adjoint operator behaves when restricted to an invariant subspace or its orthogonal complement. And what we find is that the orthogonal complement is also an invariant subspace, and that the restriction of T to either U or its complement is going to be self-adjoint as well. So this is pretty straightforward. It's a cute little proof. So let's see. So for the first one, what does it mean to be invariant? Well, yeah, let's just actually zip back over to the definition right here. So to say U is a T invariant subspace of U, that means that T maps U into U, or in other words, the image or range of T when applied to U is contained in U. Okay, so cannot write. So we must show then that if we apply T to U perp, it ends up back inside U perp. So pick something from U perp and check that its image is in the right place. So we're going to pick V from U perp and show that its image is back in U perp, right? So in other words, this last one is we want to show that the vector TV is orthogonal to all of U. Okay, so how do we do that? Well, we pick something in U and toss it in inner product and see what we get. So if we have TV U, then let's see. Well, using the fact that T is self-adjoint, we can pass it over to the other side. Actually, you know what? Here, instead of writing it as a little decoration up above, let's do it like a legit proof. Okay, and then let's see. But now I know that this TU right here is in U because of the invariance, right? And we picked back at the beginning V to be an element of U perp. So that means it's orthogonal to anything in U. So in particular, this is 0. And we're done. Okay, so that's that one. All right. So what about the next part? So for the next one, let's see. So we want to show that the restriction to U is self-adjoint. So if we take U and V from U, then throw it into the inner product with the restriction of T to U. Well, let's see. So since these elements U and V are in U, when we apply the restriction of T to U, that's just the same thing as T itself applied to them. If U and V weren't in this subspace, then there would also be some projection to U involved. But as it is, no, they just coincide. So this is since these guys are in the subspace. And then we've got that this is a self-adjoint operator. So I can move it to the other side and I don't even have to pay for it with a star. And then once again, just as in the first step, I can replace T with the restriction of T to U because we're on the subspace U. And I guess, yeah, you know what? I'm going to just edit the comments real briefly here. So, okay. So now in the first one, so this equality is because U is in there, and then this equality is because V is in there. All right. I like it. Okay. And then on to the next one. So for the Next one here, let's see. Oh, well, since the orthogonal complement is invariant by part A, the same proof of B works with U replaced by U perp. So it's BSA. And so while we're talking about invariant subspaces, I wanted to draw a picture that's probably long overdue. It's sort of, I think it's a nice way to understand invariant subspaces by looking at matrices. So suppose that we have, and this is not necessarily having to do with self-adjoints or anything else, but just to help understand invariant subspaces. So suppose V looks like U1 direct sum, U2 direct sum, U3, where these are all invariant subspaces. Okay, and so now suppose we choose a basis where we have, so E1, E2, da 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 out to En, and we order them in a way where the first ones are the basis for U1, and then the next ones are the basis for U2, and then the last ones are a basis for U3, like this. So what's going to happen then is that the matrix for T in this basis is going to split into some block diagonal matrix, meaning that it's going to look like this. Now, I don't know why I chose the sizes to be like this, whatever, but everything outside these blocks is a 0. And each one of these blocks is some, k by k or j by j type submatrix. But the reason why it has this structure is because if you multiply it by a vector, and we say, okay, let's take this vector to be from U1. What does that mean? Well, then that means that it's going to have entries here, and then everywhere else it's going to be a 0, right? Because it lives in U1, and U1 is spanned by just the first few basis vectors. And then when we do this product, what happens is, so you look and say, oh, matrix multiplication. So you multiply this by this, and what happens? Well, you have some potentially non-zero stuff here meeting up with this potentially non-zero stuff here and giving you a number, and then some stuff here meeting up with the same stuff here giving you some other number, right? But what about any other entry of this vector down here? Well, in that case, you're going to get these zeros kill that stuff. 0, 0, 0, kill, kill, kill. So everything is going to end up back in those first few, and the rest will all be equal to 0 again. And so that's showing you that this is here's the stuff that lives in U1, right? And so stuff that if you start with something that lives in U1, then what comes out is also in U1. The fact that there are zeros right here, for example, is telling you that, let me get this right now. Actually, no, sorry, that's not the one I wanted. The fact that there's zeros right here, that's telling you that information from these coordinates right here does not get passed into anything coming out over here. Okay, so let's see, and then of course there's like the whole similar picture for what's going on in the next subspace. So in the next subspace, let me redraw that same picture basically there. Okay. Now this time around, we've got we've got potentially some things in the middle here that are non-zero, but everything else is going to be zeros. And so again, when you do that multiplication from the first row right here, these guys are going to be killed off by these zeros, and these guys are going to be killed off by these zeros. So it doesn't take into, so that multiplying by this matrix, when we're looking at what happens with this, it doesn't take into account anything from the first or last rows. And then again, when we look at the output, what happens is these meeting these gives us a 0 right here, and so on. But then this meeting this is going to give us some potentially non-zero thing right here. And then again, by the time we get to the bottom, these zeros here is going to kill off everything, and then these zeros are going to kill off whatever's in here. So you're going to get, again, zeros. So the only place where you can get non-zero junk is once again in this part right here, which is coming from U2. So these are the coordinates as inputs that correspond to U2. So U2 gets mapped to U2. Okay, so yeah, that's just how to think about invariant subspaces. Again, not having to do with self-adjointness or anything more exciting than that, but just invariant subspaces in terms of matrices.